everyone. Let us now continue our discussion on first law of thermodynamics and its application of law or the first law to gases. Now, after studying this module, you should be able to accomplish the following outcomes. One is to state and apply the first law of thermodynamics occurring at different conditions. So for isothermal, isobaric, adiabatic, and reversible and irreversible changes, and describe the behavior of and calculate work, internal energy, enthalpy, and heat capacity during these state changes occurring at different conditions. Now, let us review different types of processes occurring in a closed system. So we have constant pressure, which is isobaric, constant volume or isochoric, constant temperature, isothermal, and adiabatic. There is no heat transfer. So take note that for adiabatic process, Q is equal to 0, isochoric process, W is equal to 0 or work, and isothermal internal energy or delta U is equal to 0. Now, the first law works differently for a process in which the volume stays constant than for a process in which pressure stays constant. So, as I mentioned, most of the processes are occurring in, especially in the laboratory, or are occurring in constant pressure. Though in this study, we will also be considering constant volume processes. First, let us take the isochoric process. So you know that for isochoric process, volume is constant, so the volume delta V is equal to 0. On a PV diagram, this type of process would be represented by a straight or vertical line. Therefore, there is no area under the curve. Since delta V is equal to 0, work is equal to 0. Therefore, from the first law of thermodynamics equation, delta U, or internal energy, is equal to Q at constant volume. Now, let us take isobaric process. So, in this system, the pressure is fixed, so delta P is equal to 0. So, this is represented by a horizontal line on the PV diagram, and both work and Q will exist or have values for this process. And then to solve for delta U, you will apply the first law of thermodynamics equation. Adiabatic process, so there's no heat transfer to and from the system. So therefore, delta Q or Q is equal to 0. So therefore, in terms of PV diagram, the curve of an adiabatic process on the PV diagram will depend on the change of system. So delta U is equal to work adiabatic. For isothermal, since delta T is equal to 0, delta U becomes 0, so Q is equal to negative W. And in the last part of the lecture, we will be dealing with cyclic process. So certain processes have the initial, same initial and final states. So therefore, this is considered as a closed path, and then you will realize that delta U is equal to 0. Now, let us take constant volume or isochoric. So for constant volume, you know that work is equal to 0. And from the first law of thermodynamics, du, integral of du from ui or initial to final state is equal to integral of qv or constant volume. So this is ncv dt. So therefore, the first law of the equation that we will be using is delta U is equal to QV equal to NCV dt. So this is how it is represented in the terms of PV diagram. So this is how we derive So from the first law of thermodynamics, du is equal to dq plus dw, and work is represented by negative pdv. So this is equal to 0. So work is equal to 0. Delta u is equal to qv equal to ncv delta t. Now, for isobaric process or constant pressure process, so pressure here remains constant in the PV diagram. So this is represented by a horizontal line. So we have change in volume from V1 to V2, as well as temperature change from T1 to T2. So in terms of delta U value, this is equal to N CV delta T. Now, let us derive the equations that we will be using. So starting from the first law, du is equal to dq plus dw. dw is represented by negative pdv. So example, if we will be considering an ideal gas of volume V1 and temperature T1 contained in a cylinder, now exerting a pressure of P1. So when the temperature is elevated to T2, what will happen to the volume? Volume increases to V2 while the temperature is maintained at P1. So we will be using the ideal gas equation, negative nR dt. So substituting, you know that this is heat at constant pressure. So this is represented by Cp. So du becomes Ncp dt minus nR dt. So common factor n and then dt, Cp minus r. So take note that Cp minus Cv is equal to R. Therefore, Cp minus R is equal to Cv. So that's why the equation for delta U is NCV delta T. And then you will use negative P delta V for work since pressure is constant, and Q at constant pressure is equal to NCP delta T. Now, comparing the isobaric and isochoric process, so for isochoric, work is equal to 0. Work is equal to negative P delta V. Same equations for delta U and CV delta T. Q here is NCV delta T for isochoric and NCP delta T for isobaric process. Now, more on enthalpy. So, enthalpy is another state function. So, you know that dH is equal to du plus pdv. Now, take note, for constant pressure, dH is equal, or enthalpy is equal to dQp and Cp delta T. So, the relationship of heat capacity as constant pressure is related to change in enthalpy over temperature at constant P. Whereas constant volume or isochoric, Cv could be related with delta U over delta T at constant V. Now, for changes in enthalpy, if you had the system here, so heat flow into, we have a positive value of Q. So therefore, what will happen to the energy enthalpy is equal to a positive value since this is an endothermic process. Whereas heat flow out, so we have negative Q. And what will happen to delta H? So delta H becomes negative, or this is considered as an exothermic process. Now, more on heat capacities. So, take note that for Cp and Cv of monoatomic ideal gases, Cv is equivalent to 3 halves R. So, this is how we derive from the internal energy equation as the sum of kinetic and potential energy. And since Cp is equal to Cv plus R, Cp is equal to 5 halves R. So take note that this is for monoatomic ideal gases. So if we have diatomic ideal gases, Cv is 5 halves R and Cp becomes 7 halves R. Now, let us proceed with isothermal process or constant temperature process. So, under isothermal conditions, the behavior of an ideal gas is described by Boyle's law, and the process is illustrated by the graph below. So, if we have an isotherm here for reversible isothermal expansion, so what is the difference between reversible and irreversible? So let us first discuss reversible process. A reversible expansion is carried out extremely slowly such that the external pressure is always a well-defined quantity and differs from the pressure of the gas by an infinitesimal amount. So meaning the pressure here becomes external pressure, which is equal to P plus TP. So we have an approximation here that this is the external pressure is taken or equal to P. So work reversible is equal to N RT ln V2 over V1. So we described this in the previous lecture. And Q reversible is equal to negative of work. So Q reversible becomes positive nRT ln V2 over V1. And this is how this is represented in the PV diagram. So this is equal to the area under the curve for reversible isothermal expansion. Now, an irreversible expansion takes place in a finite time. So if it occurs against a constant external pressure, P external, so we have a different value of work. So this is how it's represented in the PV diagram. So P external becomes constant here, and work irreversible is equal to negative P external delta V. So Q irreversible becomes positive P external delta V. Now, looking at the graph, you know that in terms of magnitude, work reversible is much higher than work irreversible. So this is how we derive this. Isothermal process, delta T is equal to 0. So take note, delta U and delta H are also equal to 0. And delta U from the first law equal to Q plus W. So the relationship is Q minus W is equal to minus W. And these are the equations that we will be using for reversible and irreversible process. Now, let us discuss a sample problem. A 4-liter sample of H2 gas at 1.5 atmosphere and 25 degrees Celsius is allowed to isothermally expand to a final pressure of 1 atmosphere. Calculate Q, W, delta U, and delta H if the gas expands reversibly and irreversibly. Now, based on the problem, we have V1 equal to 4 liters, P1 equal to 1.5, and pressure becomes 1 atmosphere. So we don't know V2 yet. And T1 is constant at 298.15. So using Boyle's law, we solve for the volume equal to 6 liters. Now, let us solve first reversible process. So you know that for reversible process, delta U and delta H is equal to 0. Now, we compute N first. So this is not equal to 1. N is equal to 0.245. So substituting negative N value for R, ln 6 over 4, we have negative 246.24. And Q becomes positive 246.24. For irreversible, we will be using the equation negative P external equal to the final pressure of the gas multiplied by delta V. So the negative 1 atmosphere is converted to Pascal, then 6 minus 4 converted to cubic meter. So work irreversible is negative 202.65 joules, and Q irreversible becomes positive 202.65 joules. Now, let us proceed with adiabatic process. So you know that for adiabatic, this is an isolated system with no heat flow. Okay, so during adiabatic process, so since there's no heat flow that is taking place, Q is equal to 0. So the expression for the first law of thermodynamics simplifies into delta U equal to W. So this shows that any work done under adiabatic conditions is at the expense of the internal energy. So if the system performs work, take note that the internal energy decreases and the temperature of the system will drop. And on the other hand, if work is done on the system, internal energy increases and temperature of the system rises. So the PV diagram is represented by here. So we have P1, V1, and T1, and P2, V2 in terms of T sub 2. So T1 here is greater than T2. So if temperature um, of the system rises, so work here is done on the system. So this is just an example. Now, for adiabatic process, the curve here is represented from this point to this point. This one. Now, for adiabatic reversible process, we are no longer getting the relationship Boyle's law and Charles' law. So we have a new set of equations for adiabatic reversible in terms of temperature volume, temperature pressure, and pressure volume. Now let us derive one relationship. So if T1 is greater than T2 here in the adiabatic process, du is equal to dq plus TW. Now, since dq is equal to 0, du is equal to dw. So, substituting NCV delta t dt for du is equal to negative P external dV. And this is equivalent to P of gas. So, NCV dt, so the pressure is represented by negative nRT over B from the ideal gas equation dV. So combining temperature and volume, dt over T is equal to negative R over CV, dV over V. So what is R over CV? So you know that R is C in terms of CP and CV. This is CP minus CV. So substituting R over CB is CP over CV minus 1. And the ratio between CP over CV is represented by gamma. So gamma, this becomes gamma minus 1, ln T. So the equation becomes ln T2 over T1 is equal to negative gamma minus 1 ln V2 over V1. So removing the ln, T2 over T1 is equal to V1 over V2 raised to gamma minus 1. Okay, so you could also do the same thing to derive the relationships between pressure and temperature as well as pressure volume. So for our equation, delta U is equal to work equal to NCV delta T. Now, for irreversible adiabatic process, we have a different relationship. So we have T2 over T1 is equal to P2 over P1 plus CB over R all over CB over R plus 1. Now, you could apply the equations that we have derived to solve this problem. So in the next set of videos, we will be discussing how are we going to apply those set of equations that you have learned to solve cyclic process.
Kill that bitch.